Hello and welcome everyone. Our users, this is your Module 4 demonstration in which we talk about advanced ANOVA. So this is a fun one. This is going to be broken up into two parts. So in the first part we're going to be learning about ANCOVA and the different ways to run ANCOVA and interpret it. And in the second part we're going to look at repeated measures ANOVA. So kind of extending the ANOVA framework to handle situations where we have longitudinal data collected across time, which is pretty cool. So this is the Module 4 handout, and it is the place with all things ANOVA on it. And it's available on Canvas, and it's also available on my RPub's website, and you have a PDF handout as well that is based on this code, so feel free to follow along. So we're going to start, like I said, with an ANCOVA model, and we're going to load in some packages, the tidyverse, of course, and the Haven package. The Haven package is the package that allows us to load in data from other software packages, and the tidyverse is our kind of all-purpose data management, data cleaning, data visualization tool that from RStudio that helps us do all this stuff. So the first example we're going to talk about is kind of what we'll call a classic ANCOVA design. Again, ANCOVA meaning analysis of covariance. And so this is a case where we have an outcome that we're interested in measured as a post-test, which we administered after some sort of intervention or some sort of program or curriculum that was randomized between groups. So we have more than one group as maybe a control condition and one group as a treatment condition. We could have more than one group. We could have 5 groups. That part doesn't matter. And then we administered a pretest. So before this started, we administered a pretest to all the participants. So we have a pretest score, a post-test score. So that's longitudinal data, right? The same measure across time, and we have a grouping variable that determines what group people are in. So this data that we're going to use is called HAP ANCOVA 1, and it is again a data file. So we'll take a look at this. I just loaded it in and called it HAP ANCOVA in my data set here, or in my R environment. And then we'll use the glimpse command, which I always recommend to get a sense of the data structure. So we have 82 rows, so we have 82 participants in this data set. We have 4 columns. So we have an ID variable. That's basically a row number in this case. It's not terribly helpful. It will be much more useful when we do repeated measures ANOVA. That serves an important purpose. We have a pretest score, HAP pre. We have a post-test score, HAP post, and then we have a treatment. And I believe the outcome here is a scale that measures happiness. I know that's kind of weird, right? There's a scale that measures happiness, but there actually are several kind of psychological attitude scales that measure happiness. And so we have a pretest and post-test, and then our treatment, I believe we have a comparison condition, and then we have an optimism treatment group that received some form of therapy that tried to develop a feeling of optimism. So that's our kind of treatment comparison. And we do have some labels here, so we could explore this a little bit more to see what exactly the groupings are. But before we do that, what I want to do is I want to take this variable treatment and I'd like to convert it to a factor, because I'm going to be doing ANOVAs. ANOVAs are largely based in factors, and so we want to make sure that we can work with that. So I'm going to create a clean version of this data set. I'm going to call it hapanova.clean, and it is going to be just starting with the original data set we loaded in, and then that's our pipe operator using the mutate function. So we're going to create a new variable in that data set based on a version of an existing variable. And so this is going to be called treat.fac, and that is just going to be the variable treatment converted to a factor using as_factor. So we're going to run that. And notice another data set pops up here with 5 variables. So we now have a copy of our data set with that new variable. And then we'll just do a quick summary function to make sure everything looks like it should. And this is another one. So I realize I'm showing you a lot of stuff. We've done describe in the psych package, which is a nice way to get a summary of your data set with mean, standard deviation, stuff like that. I think we've done describe from the HMISC package as well. But what I've noticed, and Erica has also noticed this too in working with me on these data sets, is that the describe package the describe function from HMISC does not function the way we would want it to. We get some weird errors. And maybe you got some of these too. And so I would recommend when that happens, falling back to something from base R. And so the summary package from base R basically does a lot of the things that the describe function does. Maybe not as cleanly or nicely, but so this is what the summary, so it's just summary, and then you can run summary on a data frame like this, ANCOVA clean. And so basically you get very simple descriptive statistics. You get a min, a median, and a max. You get a mean, and then you get, for all factor variables, so down here is our new factor variable, you actually get the labels. And so we do have 41 people in the control group, 41 people in the optimism therapy group. So here's happiness pre, happiness post. So notice the mean score at pre is about 51, the mean score at post is about 53, so it looks like happiness might have gone up a little bit on average. And then we have our treatment variable. That, of course, is the numeric version of the treatment variable. What we want to look at is the kind of factor version of the treatment variable. So I don't know, summary might be simple enough that that's what we need. So we'll go with that. All right, whenever I'm doing an ANCOVA, I always like to look and see the extent to which my pre-test and my post-test are correlated. Hopefully, if it's roughly the same test, you do have a pretty strong correlation between pre-test and post-test. That's a good thing, one, because theoretically you would expect pre-test and post-test to be correlated, and if they're not, there might be something wrong with the measure. But two, it also helps us with power if you think back to the lecture. So if you have a pretest and post-test that are correlated, then that pretest score can sometimes help to account for some of that noise, that unexplained variation in your post-test, and make it easier for you to find a treatment effect for your treatment. And so this is always a good first step whenever you're doing ANCOVA. And running a correlation is really easy in R. It's this function called cortest. And it again comes from base R, the package called stats, which is loaded up every time you open R. It's kind of one of the go-to packages. You don't even have to load it. And it's called cortest. And then what you do is you give it 2 variables to correlate. So this only works for 2 variables at a time. And you have to be very specific with the variables. You have to indicate the data set, and then with the $sign, the name of the variable. So the command here is core.test, and our data frame is ANCOVA clean. That's our data frame over here. And we're correlating happiness pre with happiness post. Notice over here, ANCOVA clean, $sign, happiness post. There are some other options here. You can get like what's called a Spearman correlation if it's ordinal data. You can get use other kinds of techniques, but this basic one is what's called a Pearson correlation, or the Pearson product moment correlation, which is pretty standard. So you get a little message here. This is a Pearson correlation. Here are the data. These are the 2 variables. Here's our t-statistic for that correlation. Just like we would interpret a t-statistic for any kind of a hypothesis test, that's very high. Anything over 2 is going to be statistically significant. We had 80 degrees of freedom, that's n-2 in our data set, and the p-value is very small, 1.3 times 10 to the negative 8th. And I'm realizing that the more and more we use R here, we have to get better at scientific notation, right? We have to sort of recognize, because R is very precise, and so it won't just tell you 0, 0, 0, right, like some other software. It'll actually give you the exact value, but this is a very low p-value. Our alternative hypothesis is that the true correlation is not equal to 0, which means our null hypothesis is that the correlation is 0. So that's kind of cool. It gives you the hypothesis built in. This is a 95% confidence interval for the correlation, and this is the actual correlation itself. So it's 0.58. So that's pretty high, right? Any correlation above 0.3 or 0.4 in education seems like it's pretty high. So it's a good sign that these things appear to be correlated. I'll pause for just 1 second. Okay, we're back. The joys of filming videos at home. So here we are, and we just talked about the correlation that goes with the prior to doing the ANCOVA, and we just found that there's a correlation of about 0.6 between our pretest and post-test. So that's actually really good. So that means when we run our ANCOVA, we're going to be able to explain quite a bit of the variability in post-test score given pretest, and really clear out some space there to find a significant impact from our treatment factor. So let's talk about running an ANCOVA. ANCOVA here actually uses the same code that we learned last week for ANOVA. So that's really nice. The code here, it's AOV for analysis of variance. And here we're going to call this ANCOVA 1 because we're going to probably do a couple of these. Our outcome is happiness post. Then we have a little tilde. And then our treatment variable is treatment.fac. Remember, it's the factor version. Plus happiness pre. So we have a pretest score in there. And then we have to tell the software what our data is, which is hap ancova.clean. So that's our data set, right? So if you're running an ANCOVA, you need an outcome, you need a factor variable, and you need a pretest score. And then we just ask for a summary of that, and it runs it for us. So here we go. Remember, in R, you get a pretty simple output. So you get a listing of each factor or variable that's included. So here's treatment.fac, and here's our pretest, and then here's information about the residuals. And then here's sum of squares, mean squares, f-test. So this is the test statistic, and this is the p-value. That's it. It's pretty simple. So for us, we just want to pay attention mostly to the p-values, although there are other things we can look at, right? But for now, we just want to interpret the significance of this test. So happiness pre is down here. It is highly significant. That makes sense because we know that happiness pre is correlated with happiness post at a level of 0.6. So those things are going to be very, very strongly related. That's not a surprise, but we want to pay attention to is the p-value. And it's right on the edge here of statistical significance, 0.059, and that is the p-value for treatment.fac. So there might be something there. It's not strong, right? It's not a super strong like p less than 0.001 effect, but it is some kind of a significant effect at the very least. Okay, so we can also do a Tukey's HSD, or honestly significant difference, with this to try and see if we have a significant differences between all of our groups. Now for us, we only have two groups. We have an optimism therapy group and a control group. And so a Tukey's HSD doesn't get us that much information. But if you had more than one group, let's say you had a business as usual, you had a group optimism therapy group, you had a cognitive behavioral therapy group, so on and so forth, you could actually do a comparison between all of those groups really nicely. So that would be really good. So this is what it looks like. You just do Tukey HSD. Again, that's from the stat package in ANCOVA 1. So you get this little message when you do this in an ANCOVA. It says non-factors ignored. That's just telling you it's not looking for differences according to the pretest, because that's a continuous variable. And then you get one difference here, which is the optimism therapy group minus the control group is equal to 3.31. So that is 3 points on the happiness scale. So optimism group was 3 points higher. And here's the 95% confidence interval for that difference. So it barely contains 0. It goes from minus 0.1 all the way up to positive 6. So remember, this is kind of a borderline effect. And then the p-value here is 0.059. So that's the difference. So again, if we had more groups, this would be really, really helpful, because it would allow us to look for differences. We can also get effect sizes here, either eta squared or omega squared, using the effect size package. So again, the effect size for the pretest is always going to be big if you have a relationship between your pretest and post-test, so that's not as helpful. But the pretest for here is the effect size for our treatment. It's 0.04 in eta squared and 0.03 in omega squared, and here's a confidence interval for that too. So this is not a huge effect. This is definitely a small effect, but there might be something there. All right, so now let's talk about a little kind of thought experiment. So let's pretend that we have this data, but in our design we didn't collect a pretest. We only collected a post-test. We can actually see what the effects would have been. We can just do a regular ANOVA, which we learned last week, for treatment. And that's what we do here. So this is called ANOVA 1. And notice the only thing that's different here, AOV is still the command. We don't have a pretest in here. We just have an outcome, post-test, and a factor. So we can run this and we can see what the results would have been. And sure enough, if we look here, this difference would not have been significant. So remember, we learned in the lecture that one of the advantages of an ANCOVA is that it allows you to control for things. And that's exactly, let me be more specific. It allows you to control for variation and account for variation in your post-test score that would previously be unexplained, which is the case here. So when we introduced a pretest score, we then were able to explain away, if you think of that pie chart, we were able to explain away some of that variation, and we were able to find a significant difference for our treatment factor, which is pretty cool. And of course, since I'm a regression guy, I want to show you how to run this as a multiple regression, and we actually get just slightly different results, which is kind of interesting. So ANCOVA is actually multiple regression. It's a specific kind of multiple regression. It's a multiple regression with one categorical variable, which is your factor, and one continuous variable, which is your pretest. But it's still just a multiple regression. So this is the same model we just ran, just fitted as a regression. So here, notice the command is LM instead of AOV, which is analysis of variance. LM is linear model. Here's our outcome again, happiness post. And this is actually identical. This equation is exactly identical as the ANCOVA and the data command. And then we just use the summary to get a summary of this. And so if you're more a regression person, and I'll be honest with you, I tend to be, this can be pretty nice. Let me see if I can make this a little smaller and then get it all to fit on one. There we go. Now it all fits on one page. So here's our call. Here is our effect for our optimism therapy group. Notice the difference is about 3 points, in this case about 4 points. And interestingly, the p-value is just a little bit lower. It's 0.03. It sort of tips over into significance, so that's kind of interesting. And here is the effect for our happiness pretest. It's about 0.6, and it is highly significant. We also get an intercept, which you don't get typically in an ANOVA, so that's the value of your outcome, the predicted value of your outcome when both of these things are equal to 0. So this would be the predicted happiness score of someone in the control group who did not receive the treatment, who had a happiness score, incoming happiness score of 0, whatever that means. I think that's pretty low. But we would expect that their post-test would be about 21. All right, R squared, we also get R squared, which you don't get in ANOVA, so we're explaining about 36% of the variability in post-test. And most of that we know is coming from the relationship between the pretest and the post-test. All right, so one other example with ANCOVA, and then we'll call it. So sometimes, the idea of collecting a pre-test and a post-test is really clean. But sometimes that's not great for external validity because the concern is that if you do that, people essentially just learn how to take the test. So there's a testing effect, right? And people sort of improve just because you gave them the same test twice. And my friends at EdSite can probably tell me exactly what that concept is. from their cognitive psych class. I can't remember exactly what it's called. But anyway, this is a phenomenon you see a lot when you have sort of a matched pretest and post-test. And so sometimes it's actually better just to collect related measures as covariates instead of a pretest. So you collect a set of related measures at pre and then an outcome at post. And so we actually have a version of this data set that does that. So I want to show you how to implement that in an ANCOVA framework. So first we load in the data set. It's called HAP ANCOVA 2. Load that in, and there it goes. It's up here. It has a few more observations, 96 observations. And then we'll glimpse this. So we have a happiness score. That's our outcome now. Remember, we don't have a pretest, post-test. We have a treatment indicator. And we have 3 measures of related to happiness, and that is satisfaction with family, overall health, and social relationships and friendship. So these are all, so we would expect all of these things to be correlated with family. And so instead of just giving a pretest of that family scale, we might give these related measures instead. So we can clean this data again, and here again all we're doing is creating a factor variable from this treatment indicator. So that again we need to redo that because this is a new data set. And then we can explore this a little more again using that quick and dirty summary function. So here's happiness, here's our old treatment indicator, here's family satisfaction, health, social and friendships, and then our treatment indicator. And so we have a nice balance between control group and optimism therapy group. Okay, so just as a thought experiment, let's figure out how much variation do all those covariates explain in our outcome. So that's just a regular regression without the treatment indicator. So here's regression 2, and it's happiness predicted by these 3 things. So are these 3 things good to include in a model? Will they give us some explained variation in our outcome, which will help us along the way? And the answer here, I see a lot of stars, which is good. So family satisfaction, health, friends, not so much, but it's close. They all seem to be related to the outcome. And here's our adjusted R squared. So we're getting about 26% of the variation in happiness scores just with these related covariates. So if we don't have a pretest, we can use these instead. And in some ways, that's actually better for external validity, which is pretty cool. And then we can dump these into our ANCOVA model. So here's ANCOVA 2. So notice now HAP is my outcome, just happiness. And I have my treatment indicator, and then I have these 3 covariates, and then my data. So get a summary of this. And sure enough, this actually works a little bit better. I do have a significant treatment effect, barely, but it's there, 0.049. And the other 3 are either significant or close, which is great. I'm not as worried about those, right? What I'm really interested in ANCOVA is the factor variable. So that worked pretty well, just to use related covariates in the case where we don't have a pretest. And then finally, again, I'm a regression guy, so I'm going to show you how to run this same model in a regression. And it's identical to what we ran in regression 2. I just add this treatment factor on here. And voila, we get our results. And they're going to be very close, if not identical. The p-values are somewhat different, which is kind of interesting. Not a ton, just a few points in either direction. So here's my treatment factor for the optimism therapy group. It's positive and significant at the 0.05 level, and it's equal to about 4 points. So that means people in the optimism therapy group scored about 4 points higher than people in the control group. And that is after controlling for family satisfaction, health, and social and friendships. Okay, so that is ANCOVA. Just to recap, we covered a lot. We talked about, in the first case, we talked about how to use ANCOVA as a way to, as a function of experimental design. And we essentially were able to control for a pretest score, predicting our post-test score, and then getting a good estimate for our factor variable. And we figured out that can really increase the power for us to find a significant group difference. We talked about effect sizes, how to get pairwise comparisons. Then we talked about this other situation down here, where what if you don't have a pretest but you have some related covariates? And we figured out that works pretty well too, as long as your covariates explain a significant amount of the variation in your outcome, you're going to get the same kind of result. You're going to be able to find a smaller but significant treatment effect. Remember, there are only 80 people in this data set, so this is a pretty small data set, which is good. And I also talked along the way about how ANCOVA models really are just kind of fancy versions of multiple regression. And so we put these things into a multiple regression model as well. All right? So that's part one of the video. In part two, we go into repeated measures, which is also a lot of fun. So stay tuned.